Okay, let's get started. This is it. We're at the last week. Yes. I believe that our final is next Wednesday. Thursday, I meant. Yes, it is. It's on Thursday. Starts at 12:30 and ends at 3:15. I don't set the times, but that's so we're supposed to be here at 12:30, just so you know. Next Thursday, right here. 12:30. I'm sorry? Next Thursday. Yep. So we do not have class next Tuesday. We have today, and we have this Thursday, and then I won't see you again until the following Thursday. All right. So we were doing 8-6 last time, right? We were doing 8-6, and I'm not done with 8-6, but I wanted to get into 8-7 today, and then tomorrow, Thursday, I'll wrap up 8-6. I thought it was important for us to start with kind of a new topic today and try and get through it, all right? So we are to one of my favorite sections in the book, Taylor and Maclaurin Series, and what I want you to remember is last time what we were doing is we were trying to take some function that was given to us and we were trying to rewrite it into its power series, right? We were trying to see, is there a way to take a function and switch it over to its power series? And the ones that we were looking at were things that look like 1 over 1 minus u. And we were able to somehow manipulate this, massage it around a little bit, and then eventually get that to turn into summation n equals 0 to infinity of u to the n, or if you want to use x, it would be x to the n. Does that look familiar from last week? Yes? Okay. This is great, what we did last time, except that it only works when your function looks like that, right? So what if you had the function like sine of x, or cosine x, or e to the x, or something like that, right? Like, you're not going to get it to look like this. So do we have a way to convert a function into its power series in general? And the answer is yes, we do. And it is this thing called a Taylor, and you'll see a Maclaurin series. So here's the gist of it. Let's say that you have a function that is defined to be a general power series. So here's a general power series, right? This is our definition. Now, with this power series, we are going to assume that it has a radius of convergence that's greater than 0. In other words, this function is defined on some interval. Otherwise, it's not worth talking about because it's only defined at one point, so who cares, right? So we need a function that makes some sort of sense. Now, I'm going to offer here as an open question to you, if all functions, right, if you have a function that can be rewritten as a power series, then as n changes, the power on this changes, doesn't it? Right? And then this changes, right? What is it that distinguishes one function from another one? Like, what is the main element of this thing that would differentiate one function from some other function? Like, what's the unique characteristic within this formula that governs one function from another? The a can be different, yes. That is different, but that's not the main piece, I guess. X is always x. No, the power is going to keep going. So keep going. You're running out of things to choose. The C sub n. Okay, look. This right here, see, look, aren't power series, the reason they call them power series is because it's basically a bunch of powers of x, right? So really what makes one function different from the other is the numbers in front of each of the powers of x, right? It's the thing in front, which is this. This is basically the determining factor. This is what will make the difference between, let's say, the function, 1 over 1 minus x versus, that's what we did last class. We could turn that into its power series, right? Or we could do 3 over 4 plus 2x. We could do that one. These both could be converted to power series, right? And when we write their formulas, the main difference between the two is this. This is always the same. This is the part that's different. Does that make sense? So the ultimate question here is, if somebody hands us a function, all right? So let's say somebody gives us a function, and we wish to put it into a power series. Is there a way that we can determine a formula for the C sub n. So let's see if we can't figure it out on our own. So do you agree with this? First of all, if we're given a power series, then f of x can also be rewritten this way. I'm going to write out quite a few of these. One more. Okay, we agree with this? That's just plugging in 0, then 1, then 2, then 3. All right, I'm trying to figure out, my goal, our goal, is to see if we can figure out a formula that will give us what the C sub n has to be. And remember, somebody has given us a function, all right? They haven't told us what the power series is for the function. They've just given us a function. Maybe they gave us sine of x or cosine x or something, right? And now we're trying to find if there's a way to determine what those numbers in front are going to look like. So this is a very clever way to do this. First of all, I'd like for you to tell me what is f of a. Can you tell me what f of a is? This is f of x, right? If I tell you to plug in a for x, what would you get? C sub 0, C subscript 0. This would be gone, right? 0, 0, 0, 0. They're all gone, aren't they? The only thing left is this. So C sub 0. Okay, so that means that, look at what this is saying. That means that if I want to know what that first number is going to be, it's actually the function that you handed me with a plugged in. So let's say I gave you sine x, right? And let's say a here was 2. Then the first number in front is sine of 2. Does that make sense? All right, well, let's continue. All right, that's great. So I got the first number, didn't I? I got the C sub 0. I wonder if we can get C sub 1, if I can figure out a way to get C sub 1. So here's how I'm going to do it. First, tell me what the derivative of that function is. What's the derivative of this? All right, well, derivative of that? 0, right? Derivative of this. So C1 is a constant. It comes for the ride. And then what is the derivative of this? 1, right? Derivative of x is 1. Derivative of a is 0. So I just get 1, right? So it's just that. Plus, okay, now, derivative of this one. Be careful here. We did this last class. We did differentiate, right? So what's the derivative of this going to be? 2 comes out. 2 c sub 2 x minus a to the first power. Then you take derivative of what's inside of here, which we already know is 1, right? So that's it. What would the next one be? 3 c sub 3 x minus a squared. Next one, 4 c sub 4 x minus a to the third. Last one, 5 c sub 5 x minus a to the fourth plus ... right? I'm trying right now. I know what C sub 0 was, right? And I told you I want to see if I can figure out what C sub 1 is. Can anybody tell me how I could get C sub 1 right here? Yeah, f prime of a. So why don't we take that derivative we just got and plug a into it? So again, what would happen if I plug in a? Kills everything off, and all you get is C sub 1. All right, so C sub 1 is the first derivative of the function at a. C sub 0 is the function at a, right? C sub 1 is the first derivative at a. Maybe C sub 2 is the second derivative at a. Maybe? Seem logical? It's not, but it seems logical, doesn't it? Okay, so let's do our second derivative. What's the second derivative of the function? So something very unique is about to happen, and we're going to hopefully establish a pattern. I'm taking derivative of this, right? So derivative of C1 is gone. What's the derivative of this? 2C2, right? 2C2. And then derivative of this one. So plus 6, right? Because the 2 comes out. I'm not going to write 6, though. I'm going to write 2 times 3. C sub 3. X minus a to the first power. What's the next one? It would be 12, right? But I'm going to write 3 times 4. c sub 4 x minus a squared, right? The next one, 4 times 5, c sub 5 x minus a, where are we at, cubed, plus dot, dot, dot. Now, if I wanted to know what c sub 2 was, I would need to kill all these off, right? So again, plug a into that second derivative. So when I plug into the second derivative a, I get 2c sub 2. Not c sub 2, but 2c sub 2. So c sub 2 would actually be that divided by 2. You'd have to divide both sides by 2, wouldn't you? Okay, but we have a way of getting c sub 2 now, right? Let's go get c sub 3. I think I'll do c sub 3 right here. So what am I going to do to get c sub 3? Take the third derivative. So if I take the third derivative, watch the way I write this. I'm not going to write 3 prime marks because I'm eventually going to have too many primes, right? So when we want to notate derivative, what we do is we put the number there and we put it in parentheses. So f with the little 3 up there means third derivative. Do not confuse that with this. This does not mean third derivative. This means what? Cube the function. Take the function times itself 3 times. With the parentheses around the 3, it means take the third derivative of the function. All right, so I'm taking the third derivative, and that means I'm taking derivative of this, right? So derivative of 2c sub 2 is 0, right? Here, we're going to get what? 2 times 3c sub 3, right? Then plus the derivative of this one. Do y'all see what's happening here? What's the derivative of this one? 2 times 3 times 4. It's starting to look like a factorial, isn't it? 2 times 3 times 4, c sub 4. And then x minus a, parentheses. Then plus the next one, which is going to be 3 times 4 times 5, c sub 5, x minus a squared plus dot, dot, dot. Now when I plug a into this, the third derivative at a is 2 times 3 c sub 3. Is that enough of the pattern to see what's going to happen? Like on the next derivative, I'm going to have what? 2 times 3 times 4, right? But when I do that, this one's going to gain the 2 when I take the derivative, right? So the next time, I'm going to have 2 times 3 times 4 times 5. But this one, they all keep doing that. So it keeps building on to the front. So can we come up with, maybe you can tell me, without us actually writing it down, what the fourth derivative at a would be? 2 times 3 times 4 c sub 4. And then the fifth derivative at a, 2 times 3 times 4 times 5 c sub 5. So really this is 5 factorial. I don't need the 1 here, right? There is a 1 there. So that's 5 factorial. This is 4 factorial. This is 3 factorial. And if you look backwards to our others, wasn't that 2 and 1 factorial, respectively? So in general, here's what I have. The nth derivative at a should be what? N factorial times c sub n, right? That's what we have concluded from this. And weren't we trying to come up with a formula for c sub n? Just solve this for c sub n. So if we solve that for c sub n, we get the nth derivative at a over n factorial. And that is what is going to be called here Taylor's formula, all right? And what gives us what's called Taylor series. This allows us to take a function that somebody hands us and to turn it into its power series. To do it, we are just going to have to figure out what this expression is. And as you'll see when we do some examples, this can be This can be easy, this can be a little troublesome. It just depends on the function we're handed, all right? Okay, so now let me put up what Taylor's theorem is. So let me erase that. I'm just going to put right here Taylor series. Okay, Taylor series says basically that if you've got a function, now there's some stuff in Taylor's theorem that I'm going to kind of gloss over without talking too much about. In order to use the theorem, your function has to be differentiable, right? Because in order to use that formula, we need to take successive derivatives, don't we? And if your function is not differentiable, then you can't do it. So there are certain functions that you could not use Taylor's theorem on, but they're few and far between for what we're going to do, all right? So if we have a power series, all right, then the Taylor, I forgot to put here, Taylor series about A, all right? So this is what this is called, the Taylor series about A, which is, we've seen that notation before, that language. A Taylor series about A is this function where C sub n is equal to the nth derivative at A over n factorial. Therefore, f of x is equal to summation n equals 0 to infinity of the nth derivative at A over n factorial times x minus a to the n. So these are the coefficients, right? These represent the coefficients of our power functions, or of our power function. For each term, we have a coefficient that is dictated by that formula. That's pretty nice, right? The way you come up with that? It's pretty nice little attack on that. Now, that's a Taylor series. Taylor series about A. Now I'm going to define something else called the Maclaurin series. Now, Maclaurin series, we don't want to overcomplicate this. All a Maclaurin series is a Taylor series with A equals 0. Have y'all ever heard that every square is a rectangle? Have you ever heard that before? Like, a square is a rectangle, right? It satisfies all the properties. So a square is a specific example of a rectangle, but you can have rectangles that aren't squares. Okay, a Maclaurin series is a specific example of a Taylor series. It's exactly when A is 0. If A is something other than 0, we call it a Taylor series about A. So if A is 2, it's not a Maclaurin. Understand? All right. So if we do that formula with A being 0, what does the function turn into then? What does this series look like? The nth derivative, that's still the same, right? Nth derivative at 0 though. See, we're going to be plugging 0 into the derivative, right? And then dividing by n factorial. And then x minus a, but a is 0, so shouldn't this just be x to the n right here? That's a Maclaurin series. Just replace that with 0 and that with 0. All right? All right, you ready to do a couple of examples? I'm going to give us a function, and we're going to come up with the Taylor series or the Maclaurin series, depending on what I ask for. All right? There were a few problems that are, I think I gave you 2 problems a couple of days ago, like that we were going to try and solve. Do you remember that? Did I do this one? Did I give you that integral? I was going to give you a quiz, remember? No? That doesn't sound familiar? No? I didn't give you this? Oh, wait. I did ask you what sine of 2 was, right? And I said, you're going to have to use your calculator to do that, right? And I said, how's the calculator doing that? Okay, but I didn't give you this one? I think I've brought it up in the past. Okay? We've done this one, right? I've shown you how we can do that with the Taylor series, or sorry, with the power series. I've shown you that that's how you can compute sine of 2. Or did I? I showed you a series that worked for sine of 2, but I haven't shown you how you can do it, like how you come up with the series. So we'll leave that as an open question. But so I'll try and answer that today, and then we will answer this today, and then I have another one that I want us to answer or be able to look at, and that's this one. Have y'all seen this one? Ever seen that before?
Yes.
You have seen that?
I don't remember.
You might run across this again in your life, depending on what you do. This is argued by people in the STEM fields to be the most beautiful equation in math. And it's called the most beautiful equation, and we all know beauty is subjective. So this is opinions. But I'll tell you why it's called the most beautiful equation in math, like why people argue it is. First of all, it contains pi, right? That equation has pi in it. We all know pi is an important number, right? It's a number that we use to calculate areas of circles, and right? It's by definition, pi is circumference of a circle divided by its diameter. That's what pi is. But we know it's an important number, right? And it's in this equation. We also know e is an important number because e to the x is the exponential function, right? The natural exponential function. That's the only function that is its own derivative, right? E to the x. So we know e is an important number, 2.718 something. What about I? What's I in our... That's the imaginary number, isn't it? That's square root of -1. And for a long time, mathematicians argued about this. Like, some mathematicians were like, yeah, this makes perfect sense, and other people were like, no, you're crazy, okay? Turns out that it makes perfect sense. Not right now. Take a complex analysis course, all right? We're just going to take it on faith that it makes sense to talk about this, all right? So I is an important number in our number system. Let's see, what are the other numbers in there? 1 and 0, so are those important? Absolutely. 1, believe it or not, has a very special name in our number system. It's called the multiplicative identity. And all number systems have structure to them, and our number system is called what's called a field. And there's 12 things that you have to have in order to be called a field. And one of the things you have to have is a multiplicative identity. You have to have a number within your set of numbers. There has to be a number in there that when you multiply any number times it leaves the number unchanged. So like 5 times 1 is 5, and 10 times 1 is 10. This is an important number. If 1 was not in our number system, then our number system would no longer be a field, all right? 0 is another one of the 12 things you have to have for a field. That's called the additive identity. This is the number that if you take any number and add it to that, the number's unchanged. So 5 plus 0 is 5, right? So within a field, you have to have these two things, multiplicative identity and additive identity. So these are all really important numbers, right? And they're all contained and connected into this equation, right? I'm going to prove that this is true, all right? I'm going to show you that this is true today. So I'll hopefully be able to convince you that that equation holds. Before I actually do it, though, can we all agree with this? That if I show you that, you'll be satisfied? Is everyone going to be satisfied if I'm able to show you this? If I show you e to the I pi is -1, you'll be happy? And you'll believe that this equation is true? Yeah? Okay. That's my goal. It's going to take me a little while to get there, right? But I will do it. And then we can do those also, these two. We can do these. All right, so here we go. First example. Find the Maclaurin series. For f of x equals sine x. Our good old sine function. I just erased the formula for her. Maclaurin series, but I'm going to put it over here. Maclaurin sum n equals 0 to infinity, the nth derivative at 0 over n factorial x to the n. All right, that's it. So what I'm going to do to start this is I'm going to try and figure out what in the world the nth derivative at 0 looks like. Because we know that this is constantly changing, right? When n is 0, it's something. When n is 1, it's something else. When n is 2, it's something else. Because the n is telling you which derivative to be looking at, right? So I'm going to create over here a table, and it's going to have 2 columns in it. And the first column that I'm going to have is going to be my derivatives of the function. And then over here is going to be those derivatives with 0 plugged in. All right? So I've got 2 columns to this. So let's start out at the very beginning. What is the 0th derivative of x? And I'm using 0 because our index starts at 0, right? So the 0th derivative means don't take a derivative, right? So isn't that just the function itself? Sine x. And what is the 0th derivative if you plug 0 into it? So what's sine of 0? 0. Okay. So the first constant that I get out in front is 0. Now, first derivative. What's the first derivative of sine? Cosine x. You're integrating, I think. So now, what's the first derivative at 0? So what's cosine of 0? 1. Okay? All right. What's the second derivative of this function? Negative sine x. All right. What's the second derivative of this function at 0? Why am I plugging in 0? Why am I plugging 0 in? Because it's a Maclaurin series. And for Maclaurin series, you're always plugging in 0. All right? So plug 0 into this, and we get 0 again, don't we? Okay. Let's take our third derivative. Third derivative is negative cosine x, right? And now when you plug in 0, what do you get? Negative 1. Okay, so when do we stop? Right now? I mean, this is going to be the problem as we progress through this. You're going to see, like, when do you stop? You stop as soon as you can establish a pattern. All right? And I think we're there, but let's just go one more derivative. The next derivative, our fourth derivative, is what? Back to sine x, right? So we're back to where we started. And so the next number here would be 0, then 1, 0, negative 1, 0, 1, 0, negative 1, 0. So you see how it's just flipping back and forth? It's going between 4 different things, right? 0, 1, 0, negative 1. 0, 1, 0, negative 1. It just keeps doing that. And that's because the sine function is cyclical. That's what we call it in math. It's a cyclical function as you take derivatives. It just cycles back through itself. All right? Okay, now, let's try and write out what this Maclaurin series looks like. So we're taking a look at that series here. Remember, this really means if we plugged in 0, it would be the 0th derivative at 0 over 0 factorial x to the 0. That's what would happen if I plug 0 in, right? Then it would be plus. Now let's plug in 1. So the first derivative at 0 over 1 factorial x to the first. I'm just writing out this formula, right? I'm not plugging anything in yet. Just writing that formula out. The next one would be second derivative at 0 over 2 factorial x squared. We're going to need a few more of these. Third derivative at 0 over 3 factorial x to the third. Yeah, we'll just stop there. Plus dot, 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 right? Now let's start plugging in the things we know, all right? So what was the zeroth derivative at 0? That sounds weird. What's the zeroth derivative at 0? That was 0. 0 over 0 factorial x to the 0. All right, that's the first term of this Maclaurin series. The next term, plus, so we get 1 when we plug in 0 there, so 1 over 1 factorial, x to the first. Now, what was the second derivative at 0? 0, right? So we get 0 over 2 factorial, x squared, plus, now what was the third derivative at 0? Negative 1 over 3 factorial. I don't need that in parentheses. In fact, I have no idea why I put that in parentheses. I don't need it. I could leave it. It doesn't matter. Whatever you want to do. That okay? Now, everything from here on out is going to start repeating, isn't it? Okay, so I'd like us to actually continue this. Let's do at least 4 more terms. So what would my next term be? Plus 0 over 4 factorial x to the 4th plus, so we just did 0, so we're now at 1, right? 1 over 5 factorial x to the 5th plus 0 over 6 factorial x to the 6th plus negative 1 over 7 factorial x to the 7th plus dot, dot, dot. I think that's good, right? A bunch of this stuff is about to go away. 0, oh, wait a minute, hold on. What's 0 factorial? 1, by definition, right? So this is not undefined. This is 0 over 1, that's 0. This whole thing's gone, 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 right? And so all we're left with is 1 over 1 factorial. I don't need to write 1 factorial. This is just 1, right? That's really like x. And then minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th. Right, that's where we stopped. And notice I started to bring the minus 1s out front. So now I've made it look like an alternating series, haven't I? What would the next term be? Plus, right? 1 over 9 factorial x to the 9th. One more. 1 over 11 factorial x to the 11th plus dot, dot, dot. Now, that is the Maclaurin series for sine. That's it right there. Do you remember me showing you the series for sine already or no? When I was having you do your calculator? Did I show you all the series or no?
You showed us that, the reason it was an odd function.
Yeah, the odd function, it's called an odd function because they're odd powers. Okay, notice that? We have odd powers. Every single one of these powers on x is odd, which is why sine is called an odd function. And that really turns out to be true for all functions. In order to call a function an odd function, its power series must contain only odd powers. To call it an even function, its power series must be only even functions, or even powers of x. Okay, one last thing. Could you please help me rewrite this in a power series form? So you got to pick up the pattern here and be able to give me the formula. Let's take the alternating first. How do you want to deal with the alternating? Negative 1 to the... You have to pay attention where we're starting. We're starting at 0 for n. So we want our first term to be positive, right? Which means we should raise this to the just n. So if we plug in 0, we get 1, but if we plug in 1, we get negative 1. Plug in 2, we get 1, right? So that works. That's going to make it alternate. Okay, what do all of the denominators have in common? These are all odd numbers, right? Starting with 1. What's the formula? Oh, and factorial. So what's the formula that would give me odd numbers starting at 1? 2n minus 1 in this no, wait, hold on. Plus 1 in this case, because we're starting at 0. So if n goes 0, that's gone, and you need 1 there. But then I need that factorial, right? And then what about the powers on x? Yeah, these are all odd again, right? 1, 3, 5, 7, 9, 11. So I could just go x to the 2n plus 1 again, right? And this is our Maclaurin series for sine, right here. Now, your book has this written for you, and we'll use that later, not right this second, but your book has a list of common functions and what their Maclaurin series look like, all right? I wonder what the radius of convergence is of this. If I asked you for the radius of convergence of this, what would you do? You would do a ratio test. The ratio test. You know what I'm saying? Limit n goes to infinity, absolute value. If you did that, you would find, I'm not going to do it here, you would find that the radius of convergence of this is infinity, which means it converges for every x, which means that this sine function is this function everywhere. So when we type into our calculators sine of 2, it's the same as replacing that with 2, 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 and going out as far as you want, computing it, and then getting some decimal. And that's what your computer is doing. All right? Okay. Let's find the Maclaurin series for cosine now. And we should get a bunch of even numbers, right? For powers. Yeah, it's going to be very close. I'm going to work through this one a little faster, so hopefully you can keep up. So we're going to start here back at this table. Right? But we're starting with cosine, right, to start? So when I start with cosine, at 0 it's what? 1. And then when I take derivative of that, negative sine of x, and I get 0. Take derivative of that, negative cosine of x, I get negative 1. Right? And then the next one, third derivative, would be negative sine x, no, positive sine x, which would be 0. And then it's just going to keep repeating, right? 1, 0, negative 1, 0, 1, negative, right? Okay, so if I go to write this out, let's see if we can do this without me having to rewrite this whole thing out again. If I start by plugging in 0, then that means I'm saying cosine of x is equal to, you tell me. Starting with, so 1 over what? 0 factorial x to the 0. That's the first piece. Plus, now go to the next number, 0 over 1 factorial x to the first. Next one, negative 1. So can I put minus 1 over 2 factorial x squared? And then one more, and then it's going to start repeating. So plus 0 over 3 factorial x cubed. And now it's going to start repeating itself, isn't it? I don't think I'm going to write any more down. Can I just say dot, 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 like that? So this is the power series. Let me kill off the things that are zeros. Those are zeros, right? So what's my first term here? 1, x to the 0 is 1, so that's 1. And then the next thing I have is minus 1 over 2 factorial x squared. That's this one. What would have been the next one? One over 4 factorial, so it would be plus, right? 1 over 4 factorial, x to the 4th. Then what would the next one have been? Minus 1 over 6 factorial, x to the 6th, and so on and so forth, right? All even powers. All even power. You might argue that's not an even power, but yes it is. X to the 0, 0 is even. So these are all even powers of x, aren't they? Okay, can you give this to me in its sigma notation? You might want to look back at this one right here. So we're going to alternate, right? So negative 1 to the n again, over. My denominators are even, aren't they? Even factorials, starting at what? 0, right? So 2n, good. 2n factorial. Right or wrong? Wrong. Parentheses around the 2n. Have to have it, right? There's a difference between 2n factorial versus 2n factorial. What's that? Yeah, only the n here has the factorial on it. So if I ask you right now to plug in 5, right? This would be 2 times 5 factorial. 2 times 5 times 4 times 3 times 2 times 1. But if I said plug in 5 here, this would be 10 factorial. 10 times 9 times 8 times 7 times 6 times 4 times, right? They're not the same. They're different. And what we want are all evens. So 2n, then the factorial. All right, and then what about x? X to what power? 2n. There's your Maclaurin series for cosine. Okay? All even powers. Let's do another one. How about our good buddy, e to the x? E to the x. So e to the x, see what these derivatives look like. Well, first we start with e to the x. We don't take its derivative, and then we plug 0 in. And e to the 0 is 1. E to the 0 is 1. And then we take the derivative of e to the x, which is e to the x, and then we plug in 0 again. 1. And then we just keep doing this forever, right? 1, 1, 1, 1, 1, 1, 1, the whole time. So that means when I go to rewrite this, e to the x, I start out by plugging in 0 into this, right? So what would I get? The first number there, which is 1, over 0 factorial, x to the 0, right? Plus, there's no alternating here, right? Just 1, 1, 1, 1, 1 the whole time. So when we plug in 1, let's see, 1 over now 1 factorial x. Next one, 2 factorial x squared. Next one. And it keeps going, right? Nothing cancels, nothing alternates, right? Let's rewrite this. This is really 1, isn't it? 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus dot, dot, dot. That's e to the x right there.
So how is 1 over 0 factorial still 1?
Because 0 factorial is 1 by definition. When we define factorials back, I said 0 factorial is 1.
So I remember now.
And then we got into not argument, but I said it's hard to show, but you can have factorials for fractions, but it's a different function, so we're not worried about it. Trust. This is one of those times where I just need you to take me on faith. Take it on faith. Okay, can we get a sigma notation for this, please? What's the sigma notation for this going to look like? So it's always 1 on top over. My factorials on the bottom are just you know, sequential, 0, 1, 2, 3. So it starts at 0, right? So n factorial on the bottom. and then x to the n. See, we don't have to jump by odds or evens or anything. It's just super clean. Yes?
Would it be wrong to rewrite it like with the x to the n?
Oh, no, that's fine. You can put, you mean where the 1 is, just put it there? Yeah, that's fine. Yep. Okay, real quick, just kind of a cool thing. I think I may have showed you this already. If I did, I'm sorry. Remember that this 2 factorial means 2 times 1. This means 3 times 2 times 1. This means 4 times 3 times 2 times 1, right? That's what that is? Now, if I ask you to take derivative of this, what is the derivative of this? So what's the derivative of that? What's the derivative of that? What's the derivative of this? So 2 would come out and cancel with that 2, right? Ignore the factorials. So what would you be left with? Just x. So then what would the derivative of this be? 3 would come out, cancel that 3 out. You'd have an x squared on top, and what would be left on the bottom? 2 factorial. And then what would the derivative of this one be? So 4 comes out, cancels with that 4. You'd have x cubed over 3 factorial. And what is this? It's the same thing. Right? It's the same thing. The derivative of e to the x should be the same thing, right? It's the only function that does that. There's no other function that does that. This is the only one that does it. Isn't that pretty cool? All right. Oh, you know what would be pretty mind-blowing? Is if you took the derivative of sine. Ooh, I haven't done this one before. Oh, yeah, let's do it. This will be fun. Okay, look, real quick. We just said that what was the power series for sine of x? And don't give me the sigma notation. Give me the other notation.
1 over 1 factorial
Mm-hmm.
x to the 1 plus negative 1.
So it was x, right? That's 1 over 1 factorial x to the 1. And then minus 1 over 3 factorial x cubed, right? Plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th plus dot, dot, dot. That's the derivative. That's sine. Okay, take its derivative. Take the derivative of this. What should you get? Cosine. Let's see. Take derivative of that, we get 1. Okay, remember that's a factorial, right? So when the 3 comes out, it cancels just with the 3, and we're left with the 2 factorial down there, aren't we? So minus x squared over 2 factorial. Here, same thing. 5 comes out, kills off. We still have a 4, 3, 2, 1. So that's going to be plus x to the 4th over 4 factorial. Next one, minus, same game. Does that not blow your mind or what? That's cosine. Cosine is all evens, right? If you go back and look at we just wrote cosine out. That was exactly what we wrote. All right. That's fun stuff. All right. I think it's more fun for me than you. I'm getting that feeling. All right, you ready to see this? Most beautiful equation? Let's do it.
What does it do?
What does what do?
The beautiful equation.
It doesn't do anything. It's like when you write like 1 plus 1 is 2, like that is a true statement, right? Like we agree that this is true, right? This is truth in front of you. Well, so is e to the I pi plus 1 equals 0. This is truth. This is a true equality. Seems weird. It seems weird that e to the I pi can turn out to be negative 1. Does that not seem strange to you? That e to the I pi would turn out to be negative 1? It seems strange to me. I mean, what does the graph of e look like? Doesn't it look like this? That's e to the x, isn't it? I'm telling you that for this equation to be true, e to the I pi somehow has to turn out to be negative 1. But there's imaginary numbers involved here, so there's more in the background happening than is easy to convince you of. But somehow this number right here turns out to just be a nice integer, negative 1. So I'm going to show you how right now. But it does nothing. Okay, it does nothing. The equation is just a result of of the way things are, all right? Like 1 plus 1 is 2.
Wait, so someone just came up with this equation just for one?
It's not even like, if you ever take a course in complex analysis, which I don't think many of you will unless you're a math major or unless your engineering program involves getting into the imaginary numbers, it's actually a very trivial result that I'm showing you. But to be able to show it to you right now with you having no knowledge of imaginary numbers, you have no idea what complex analysis or complex functions look like, or I can still show you that equation is true. All right, so that's what makes this kind of cool. All right, you ready? Let's just remember real quick. E to the x, we just said, was 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus dot, dot, dot. That's e to the x, right? Okay, then according to that, what would e to the I pi be then? Well, in this case, I pi is taking place of our x, right? So let's plug I pi in for x and see what happens. So we get 1 plus what? I times pi plus I times pi, that quantity squared, over 2 factorial. Keep going. I times pi cubed over 3 factorial plus I times pi to the 4th over 4 factorial. I'm going to keep going because I need a few more to be able to establish something that's about to happen. I pi to the 5th over 5 factorial. I pi to the 6th over 6 factorial. I'm just going to go out and do like the first 26. I'm kidding. I'm just going to do 8, okay? I pi to the 8th. Let's just go out to there. Okay, 8 factorial plus dot, dot, dot. That's what it is, right? Yeah? Okay. Now, before I continue, just have to make sure we're all on the same page with something. I, by definition, is the square root of -1. That's what I is, all right? By definition, that's what it is, right? Okay, what is I squared then? -1. Again, if we square the square root, you get what's underneath, right? So this is the definition. I squared would be that. You probably have never thought about this, but what's I cubed? Wouldn't it just be, this is I squared, right? So I cubed is just this times another I. So what would happen if I take -1 and multiply it by I? Wouldn't I get -I? Is that all right if I just write it like that? That's -I. Now, what would I to the 4th be? Well, this is I squared squared, isn't it? Right? And that's I squared. So if I square that, what do I get? 1. Okay? Now, what's I to the 5th power? It's the first I, isn't it? Because look, I to the 4th, if I multiply it by another I just do 1 times I, and I get I. So I'm back to I, right? That's what's I to the 6th then? What's that times another I, which would be an I squared, which would be -1 again? And then what would I to the 7th be? Well, that times another I, which would be -I, and then if I do I to the 8th, that times another one, wouldn't I be back to here? See, I did this intentionally. I put them like this because it's like you get I, right? I squared is -1, I cubed is I to the 4th is 1. And then as you move through the powers, 5, 6, 7, 8, you're going to repeat the pattern. I, -1, I, 1. It's cyclic, right? All right, now, let's go back here. Let's rewrite this. This is 1 plus I pi. Okay. When I square this, I square the I and the pi. When I square I, what do I get? I squared? -1, right? So I'm going to write this as minus pi squared over 2 factorial. Is that fair? Okay, so the pi still got squared, the 2 factorial still there, but the I squared was my -1. Boom. Okay, next one. What is I cubed? Negative I, right? Negative I. So watch how I write this. Negative I pi what? Cubed over 3 factorial. So I brought the I cubed out front as a negative I because I cubed is negative I, right? Keep going. Plus, what is I to the 4th? 1, okay? So I'll just have here what? Pi to the 4th over 4 factorial. I know this looks weird, just follow me through here. All right, back to I to the 5th now. I to the 5th is I basically, right? So I can replace that I to the 5th with I. So I'm going to put it out in front, I, then pi to the 5th over 5 factorial. I to the 6th, -1. So I'm at -1, so I'm going to put negative pi to the 6th over 6 factorial. What about I to the 7th? Negative I. So I'm going to write negative I and then what? Pi to the 7th over 7 factorial. One more. What was I to the 8th? 1. So really just what? Pi to the 8th over 8 factorial. Okay. That looked pretty bad, right? What does this, and this all have in common? They all have numbers? They all have eyes, don't they? They all have eyes in them. The things that don't have the blue do not have eyes, right? Okay, so I'm going to write this down. I'm going to rearrange things. I'm going to write all the things that don't have eyes first, and then the things that do have eyes. So the things that don't have eyes, 1 minus pi squared over 2 factorial. What would be my next piece that doesn't have eyes? Plus pi to the 4th over 4 factorial. Do I have another one? Minus pi to the 6th over 6 factorial. Any more? Plus pi to the 8th over 8 factorial. Plus, and then there's an infinite number of those still out there, right? Okay, so I'm going to just close that off. That is just the stuff that doesn't have eyes. But then next to that, I have plus, now the stuff that does have eyes. Now, there's a bunch of things that have eyes, right? Like this has an eye, this has an eye, this has an eye, this has an eye. So I'm going to factor the eye out. And then what would my first term be if I factored that eye out? Pi. Next piece. Minus pi cubed over 3 factorial. Plus pi to the 5th over 5 factorial. Minus pi to the 7th over 7 factorial. Plus dot, 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 right? Do you recognize this? This is, which one is this one? This is cosine, but this is not cosine of x. This is cosine of pi, isn't it? And this is not sine of x, this is sine of pi. So this is saying that the answer, right, e to the I pi is equal to cosine of pi plus I times sine of pi. And what is sine of pi? 0. Pi is there, y coordinate, 0. What is cosine of pi? -1. Right? There it is. That's pretty nice, huh? So you rewrite e to whatever power, you write it out in its Maclaurin